I'm going to present some of my work on spatiotemporal modeling and in particular prediction. So I'll try to give a bit the motivation of what I'm doing, and I'll try to start from the very basic model to build on that in order to try to introduce heterogeneity in the prediction. So, like, part of my research is based on spatial data, spatiotemporal data, and these are a type of data set that are becoming more and more popular. So with spatial data, we define a very large type of data. They are usually georeference data. That means quite broad, like it's a broad definition because it can be like specific geographical areas, or it can be with locations, and we can consider not time as well. So spatial data describes a surface, and usually we have variables in a two-dimensional plane, but it could be like even more complicated than that. And there are applications in many areas of research. We have, for example, meteorology, climatology, ecology as well, but also other sides of like research, like economics, epidemiology, etc. So they're very, very popular in many contexts. For example, if like we want to study, so one of the things that happens is that what you observe is may change a lot over space, and the type of dependence is not necessarily linear or simple. So for example, if we study temperatures, like the data can come as daily measurement from monitoring stations, and what we obtain is a surface depending on these measurements. But what we have also observed is that there could be there is some heterogeneity because we can, like, there are many factors influencing the temperature, or it could be rainfalls or many other type of phenomena. But there are many factors influencing temperatures. So it means that we can't control for all of them. We may not have them in the data set that we have. And so there are too many variables to control to have a full prediction. So there are several things that we can do with this type of data. One is trying to model some trend or representing the correlation among locations or areas. And in this setting, we may want to estimate some parameters of these models. Another point is to compare several models that may be good to fit what we observe. But a popular goal is to actually make predictions in the future or in non-observed sites. So for example, if we go back and we have monitoring stations, and this is, for example, very common for all the meteorological variables, but also for pollution, for example, we may want to have an idea of the prediction over all the surface under analysis. So I'll talk a bit, like, say, I'll introduce a bit modeling, but then I'll use that to make predictions. So the basic format for georeference data is in this way. So we have two variables. One is the measurement that so the response variable that we are observing and we want to study. And this is observed at a location S. And this location may be, as I said, defined in many different ways. It could be coordinates, so longitude and latitude. It could be bigger than that, like it could be in 3 dimension. It could be an area. So it's generally defined in some space D. And we have n observations of this pair. So, for example, one thing that we may want to do is to build a continuous map on this surface D. But like how to do that is like there are many different models to do that. So first of all, we need to study spatial correlations, and these spatial correlations is like a big simplification if we can represent these correlations in terms of distances. So an important tool to do that is to study the semi-variogram. So we have a distances like between measurements. Usually it's in square terms. And we want to study the expected value of these distances between measurements or square distances between measurements. And this expected value depends on a distance row between locations. This is the ideal case because it means that the correlation doesn't change, like may not necessarily, it only depends on distances. It may vary in different distances, but it's quite a simplification. So we suppose that, so what happens here if the expected value has this form, it means that as the distance goes to infinity, we have that the expected value is constant and can be represented with this sigma. So the semi-variogram, it's a semi-variogram because there is a half here, is a graph like this. So we have this square distances on the y-axis, which depend on the distance. And depending on the type of semi-variogram, we have different models. So for example, this model can be linear. So there could be an increase as the distance increase. Many times there is a form like a shape like this. So we have an increase at the beginning, but then there is a stabilization at a certain point. And the degree of this, so the way in which this function becomes like stabilizes may give you the model, the type of model, the type of spatial model to use. So if I want to represent the model, so if the goal is modeling, one of the things that I can do is to represent the measurement as a function of the location plus an error term. And these error terms may be mutually independent. They may also depend on the space, but like as a first case, we can use mutually independent errors. And this function often is considered as a realization of a Gaussian process. The Gaussian process is often considered as stationary with a mean and a variance that do not depend on the specific location and a correlation function that only depends on the distance between locations. And so we have a variance for the Gaussian process, which is a variance of this function f. And then we have a variance component from the error term, which is a measurement error. So like it's already quite flexible as a model because then we can choose the function of the distance between location in several ways to define the different variograms that we may want to use. And there are many different types of variograms and correlation function in the literature. Some of the most famous ones are the Matern or the Gaussian, the exponential, etc. So in this talk, I'm going to focus on a Bayesian analysis of this type of model. So you can so in terms of estimation, you can do several things. So you can focus, so you can define the model in this way. So you suppose that f is a Gaussian process and you have a particular type of model for epsilon. And then it means that you have several parameters that you can estimate. And there are several ways to estimate that, for example, through maximum likelihood or some types of maximum likelihood algorithm like REML. So restricted maximum likelihood, or you can work in a Bayesian setting. So the main advantage to use a Bayesian analysis is that it's easier to take into account uncertainty in parameter estimation. So just to have a brief introduction to Bayesian analysis, the idea is that we want to derive a joint model for both the parameters and the measurement, so the response variable. This joint model means that the parameters of the model are considered as random variables as well, and so we can define a prior distribution for them. And then we can combine this prior distribution with the likelihood for the measurement, which is given from this model here, to derive a joint distribution of both the observations and the parameters. And this joint distribution is then used to define a posterior distribution by renormalizing. So we want the posterior distribution of the parameters given the observations and the locations. In this way, we can start from a prior distribution and update our knowledge about the parameters by using the likelihood and the observations. So like in this way, what happens is that we can describe the uncertainty about the parameters, and we can transfer this uncertainty from the parameters to future predictions. So we can incorporate much better the uncertainty of the estimation process into the prediction. And I'm going in a moment to what I mean with that in a mathematical sense. So I talk about modeling, but a common approach to problems of modeling surfaces is kriging. So kriging is trying to, so it's using the model that I've just introduced, which is a Gaussian model, in order to have a prediction over a surface. So we have a standard error. So the model is quite simple because we just has a measurement error. And then we trying to predict this surface over all the spatial location. So kriging is extremely used in spatial statistics, but it's a very smooth way of prediction. It means that changes over the surface will be quite smooth. So there are some assumptions in this type of modeling. One, of course, is Gaussianity. Another one is stationarity. So the correlation just depends on distances between locations. And we also want stationarity in terms of the mean. So the mean doesn't depend on the location. We can use kriging to do Bayesian prediction. So for example, let's suppose that we want to predict the surface on a new location. So the measurement on a new location, given the observations that we have. This can be simply done via integration. So by using the posterior distribution for the parameters that we have for the model, we transfer all this uncertainty into the new prediction, and it means that we are averaging over the uncertainty that we have around the parameters. So the new prediction, so the prediction of a new observation on a new location, given what we know in the rest of the surface, will be obtained by averaging around the uncertainty of the parameters. So if we use a gradient model, then it means that the future observation will be still normal, depending, for example, if we have extra covariates on a regression term plus a mean, and a variance, which is a component of the variance depending on the Gaussian process, and a component of the variance depending on the measurement error. And this C is a matrix depending on the distance between locations. But as I said, kriging is quite a big assumption. Like it can work in many contexts, but it's still working on some assumptions. And one of these is Spatiality. So it means that you create for every possible location a possible normal distribution on it, on the measurement. And this means that the change from a location to another are quite smooth. And there are no, there are no drastic change between one location and the other, unless the variance is very high. So a different type of model that so for example, what happened is that, like, if the area is affected by many different variables, that could be ocean, like ocean winds, or like the desert, or any other type of winds or characteristic of the of like geographical characteristics like mountains, etc. So if there are many different factors, it may happen that the changes between a location and another are much more heterogeneous than a Kriging model could help for the modeling. So a first relaxation of the Gaussianity assumption is to actually consider a mixture of Gaussian distributions instead of just Gaussian distributions. So a mixture of Gaussian distributions is a convex combination of Gaussian distributions. So there is still Gaussian distribution, but there are several of them. There are big capital K of them, and each of them is weighted with a weight pi. So it means that each location and each measurement for each location can be part of a different Gaussian distribution. And this can help in incorporating more heterogeneity in the model. And again, all the parameters, so we can notice that there are more parameters because there could be like one parameter, like one different type of parameter for each component. So now the regression term depends on the particular component as well as the trend and the variance. And again, there could be some of these parameters depends also on the location. I put the most general case here, but like some of these parameters may not depend on the location. And there is an additional parameter, which is the weight. And so we have, again, capital K, or actually capital K minus 1 of these weights, because the last one is deterministically determined. So we have a much more complicated model. That means that it's more complicated to estimate, but this can include more heterogeneity in the model. One of the main problems with this model is that if we define a finite mixture model, we need to define this K as a specific number. So we have to identify a reasonable number of components in the mixture. And it may not be easy. And there may be a big difference by considering different types of K. So like in particular, prediction may be affected by how many components you consider. And it may be, so in particular for complex models where these parameters depend on the location, it may be difficult to identify the correct number of components or the ideal number of components, because then we have a very few observations for each location, possibly just one. So it's difficult to identify the exact number of components. An alternative is to use a nonparametric approach. And in particular, a popular one is a Dirichlet process approach in Bayesian statistics. So the first step is to define a Dirichlet process, and then I'll go on and define a Dirichlet process mixture model. So a Dirichlet process is a process to define a process for a random distribution. So we suppose that the observations follow a random distribution. And this random distribution has realizations which are Dirichlet distributed. So for each finite set A1, AR, we have that these are Dirichlet distributed, which is, let's say, a complicated definition. But the idea behind this is that I consider K, capital K's, as infinite. And then I have a construction of these weights, which is, so I know that the maximum, so the sum of all the weights have to be 1 because they have to sum to 1. And then I have each of them, so I'll try to build them in a way where they can be infinite, but they have to sum to 1. So let's suppose that I have a stick, which is of length 1. Then I can have the first one, the first weight is simulated in a way that it's smaller than 1. And then the second is part of the remaining stick, etc., etc., etc. So this is what is called a stick breaking representation of the Dirichlet process. And the idea is that if the random distribution F is a Dirichlet process, then I can simulate values like beta random variables and like corresponding locations. And then I have that the first weight is actually equal to the first variable simulating from a beta. And then the remaining weight follow this rule where it means that from the remaining part of the stick, I'm simulating a beta, which is reweighted for that remaining part, for the second one, and then for the third, etc. And so the unknown distribution is actually a mixture between atoms simulated from a fixed distribution F0 and weights which are created in this way. So I can define this in terms of atoms. So I assign a weight to a specific atom, and I have an infinite number of this. But I can also do it by using, instead of an atom, a normal distribution. So I would have an infinite mixture of Gaussian distributions with weights described by this construction. So if I have observations which are defined on a surface, so I have observations which are indexed by a location. And as I said before, this can be coordinates, but this can also be areas, for example. The model that I'm thinking of is a model like this, where I have this mean factor, which is the spatial effect. I'm just using mu because it is the F that I had before, like here. But in this case, I have a specific mean which changes with this location. I can have a regression term, and I have the error term, which is a measurement error. So I focus on how to construct this spatial effect. And it means that I suppose that the mean effect follows an unknown distribution F, which depends on space, on the specific location. And is a probability measure over a certain space. So I can represent the distribution of the observation as an integration with respect to this particular unknown distribution. And to build the distribution of this spatial effect, I use the same construction as before. But how to introduce the space, so the locations for the specific weights. So in order to create heterogeneity, I want to not only create a composition of a convex combination of distributions, but I also want that the weights depends on space. So to do this, instead of directly having beta distribution random variables, which are independent, I have the same type of construction as before, because this weight has to sum to 1 anyway. But another point is that I want these weights to depend on the weight, sorry, on the space. So I reweight the beta random variables with a kernel-specific function. And this kernel-specific function can be described in many different ways. And then again, I associate each weight with some atoms defined on a distribution at 0. So the weights of this construction may be different, as I said, different types. I'm putting here 2 examples of that. So the uniform kernel, the square exponential kernel. The idea is that, let's suppose that we have georeference data on spatial locations. So we have longitude and latitude. So we have 2 components. This kernel depends on some knots. So it's like, so the prediction comes from dividing the surface into a grid, and each element of this grid is represented by a location or a knot psi. And I have like 2 components for each location, which are defined as longitude and latitude. And I want to define the kernel depending on the spatial location that I'm considering with respect to where I want to predict the phenomenon. So the psi gives me a localization of the surface into this grid, and I want points close to the location to be more important in the prediction than points far from that. So this is why the kernel is defined on a distance between the observation, so the location of the observation and each of the points in this grid. So given this location, it will be easier to predict points close to it than points far from it. But this will be repeated for any possible location. So if I use this construction, the construction is this proper. That means that the unknown f is actually a probability measure. Only if the expected value of the variable, the constructing variables vk is positive, which is easy to do if I use a beta distribution for them. And the second assumption has to be that the expected value of the kernel has to be positive. But again, this is easy to get if I choose the kernel like reasonably. So if I use a kernel which depends on the distances, like on the absolute or square distance, the expected value is then positive. So it means that the spatial stick breaking can be provides a well-defined probability measure. That means that the sum of the weights is equal to 1, and f is actually a distribution. F of s is actually a distribution. And as I said before, like this type of kernel based on some distances between knots on a grid is such that it, so 2 distribution at 2 different locations, at 2 different locations allocate similar probability to the same atoms. So it means that 2 distribution in 2 close locations will be more similar than 2 distributions at 2 different locations. Now, let's suppose that I'm not just interested in, so I don't have just spatial locations, but I also have time. So I have a spatio-temporal model. The type of model is very similar, but now I want an unknown distribution FTS, which is defined on both time and space. But I still want a distribution on the observations, which is defined in this way. So with respect, as an integration with respect to this unknown distribution for both time and space. So the model is defined in a similar way, but I'm adding time to each of the components. Now, what you can do is still to use an infinite mixture model, but now in the construction of the weights, you would like to have weights which depend on both space and time. The extension to consider also time, it's not immediately easy because it depends. So you want a weight which depends on both space and time. You can consider separable kernels. That means that you can consider that this weight, so this kernel is just a product of a kernel over space and a kernel over time. And so, like, instead of considering a joint grid on space and time, you consider like a grid for space and a grid for time. And even if the kernel is separable, it doesn't mean that the covariance structure is separable. So it means that like the covariance won't just depend, won't just be defined as a product between a spatial component and a temporal component. In particular, the conditional covariance, so which is the covariance between the observation at time t and space in location s, and the observation at time t prime and location s prime, like independently from the formula, which is a bit complicated. But so this covariance, like depending on the grid that you are using, is actually defined as depending on factors which are just products of spatial and temporal components. But overall, this is not just a product between a spatial part and a temporal part. So the covariance is not separable. But if I look at the unconditional covariance, so by integrating out the grid, again, I see that there is a product of a spatial component and a temporal component, but like overall, this formula is not just a product between a spatial and a temporal component. But what happens is that each part just depends on the distance between locations and the distance between times. And so there is a type of symmetry. So this is the covariance depending on different distances in times and distances in, space and time. So if two observations are close in space and time, the covariance will be very high. And if two observations are far in space or in time, the covariance will be large. Sorry, will be very small. So it means that processes at the same location or close location will be more similar. But the fact is that there is a sort of symmetry because the time and space will have the same effect in defining the covariance structure. So it doesn't mean that it represents every possible problem. And so it's again an hypothesis. A much more general approach is to consider instead a kernel which is not separable. That means that time and space are together in all this function. So you can't separate the effect of space and time in the definition of this kernel. So you have a more complicated expression of this function and more parameters as well. But it's interesting. So it's a much more general process. And the interesting thing is that this parameter lambda controls the type of space-time interaction. And if lambda is equal to 0, the model is separable. That means that, so the kernel is separable. That means that space and time participate in this kernel just as a product. So there is a spatial component and a time component separated. And as lambda goes to infinity, sorry, to 1, space and time, the space-time interaction increases. So you can make inference on this lambda parameter by trying to understand if it's closer to 0 or is exactly equal to 0, or if it's more positive. And if you do this, of course, the covariance structure is going to be more complicated. But on the other hand, so this is just to give an idea of the type of formulas you are involved with. But it's much more interesting to see that depending on the choice of kernel, like for the most, so if you use a kernel like this, like with some type of distances on the space, it's still a kernel that depends on the distances between spatial location, but it doesn't only depend on the distances between times. So you may have a much more general type of kernel where there is an interaction. So it's not as symmetric as before, the type of covariance, because there could be an interaction between time and space. And the big difference is that it depends on where the time is recorded. So it will be different if it's a time close to now, or it's a time recorded like 10 years ago, for example. And as I said before, you can actually do inference on the parameter lambda to study the separability between space and time in the kernel, for example, by using a spike and slab prior. So a spike and slab prior is a mixture of a distribution and a Dirac mass at 0. So it means that we test the hypothesis that lambda is exactly equal to 0 or it's positive. So we can use, for example, so it's a model where you can select. So you can suppose that lambda is exactly equal to 0 and it will be the Dirac mass, or it's positive and you can use, for example, a beta distribution because it has to be smaller than 1. So it's something that, so with this type of modeling, like you can test the separability of space and time in the kernel as well. So I ran a bit of a simulation study to study the performance of this type of model. And I did with different types of assumptions. So I studied like with simulations with different type of covariance structures. Like an easy Gaussian covariance. So it was a model without a trend and just with a Gaussian covariance. A model with a trend and an exponential covariance. And then some more complicated models, like just by playing on the covariance structure, or introducing some type of non-separability between space and time, for example, with a Stein covariance model. Or also like a still stationary covariance model, but space isotropic, or like introducing some local anisotropy. So like, let's say that from 1 to 6 is more complicated, like you increase the like how the model is complicated. And then I started just the prediction error on the observations. So if I just compare like the classic gradient model with just a model considering a spatial kernel and temporal observations, with a model considering also a kernel which is spatio-temporal, which is the last one I presented, I can see that for the Gaussian model, like all models are like, so this is an error. So the smallest the better, the smaller the better. So for the Gaussian model, like all models are okay. Of course, as expected, the Kriging model, which is smooth and is meant for the Gaussian case, works better. Then I have that for the stable process, the spatio-temporal. So the more complicated is the process where I generated the data, the better is the performance of the spatio-temporal stick breaking. And in particular, if a space and time are not separable, I have that this model is the best one. So the more complicated is the model where I've generated the data, the better is the performance of the spatio-temporal stick breaking. I've also applied the data set, the models to a specific data set of temperatures collected between 1985 and 2004 in California. And data were coming from NASA. So I'm just plotting, so data were for every month, but I'm just plotting July as an example. But then I model every month for all the 10 years. So what we can see is that there is a spatial component. So we have that these points here have a higher temperature. There is some similarities here, and there is a temporal trend as well. So even if these are the highest temperature, then it seems to, the following year, it seems to decrease and then increase. But like, so there is a temporal trend, I would say, but it's also spatial. There are also some spatial characteristics. So if I use just a Kriging, and then I'm trying to predict year 2004, and I'm trying to understand the differences. So the points are the actual observation in year 2004. And then the gray line, so the gray area is my prediction. And the lighter is the lighter the gray, the cooler the temperature, the more dark, the higher the temperature predicted. So you can see that with the Kriging model, the surface is very smooth, so there are not many changes between a location and another. With a spatial, so by using a spatial model, so with a spatial kernel and just atoms changing over time, it's different. So I have that here, the area is lighter because temperatures are actually cooler. And here the gray is darker because as expected, temperatures are higher. However, there's still like, it's still quite smooth. And with a spatio-temporal model, there is much more heterogeneity. So there is much more changes even within the same locations. And if I look at the computed expected error, definitely the spatial stick breaking was the one with the lowest error in prediction. So just to conclude, like when we model spatiotemporal phenomena, like there are many components that can affect the phenomenon. So like basic models based on Gaussian processes are very popular, but they also tend to over-smooth across the surfaces. So one way to avoid this is to introduce some type of interaction between space and time to incorporate the space and time interaction in some way. So the type of model that I have just proposed where you create an unknown distribution, so like a mixture model. So an unknown distribution that can be represented as a mixture models where the weights of this mixture have a space and time interaction. can help and allows to model non-stationary models and also highly non-normal models. And the main point here is that, like, it may, so depending on the data set, you may have space-time varying covariates, but you may also not have them. So like this particular model doesn't need any type of space-time covariates, but you can add that if you want and if you have it. So you can, so I've only worked by considering, so I just focus on the weights, if I can find it. Yes. So I can just, I focus just on the weights. That means that I just work, so if I represent this distribution as a mixture like this can be a Dirac or can be a normal distribution. I just put the spatial component here, but you can also include a spatial component for the atoms as well. One thing to consider is, for example, is it necessary to consider seasonality? Of course, if I look at this data, so I'm looking just at July, and all these plots are very similar because I'm just considering July. But if I consider like every month, like probably each July would be similar. So July 1995 will be more similar to July 1996 with respect to July 1996 and January 1996. But the seasonality, so you can include seasonality in the model, but also this model is flexible enough to change over time and like during the same year. And this is probably why the prediction error is so low with respect to the other models. And last thing, before finishing, is that it's a very flexible model. But one thing is that, so what I'm actually modeling in this representation here is I'm modeling a kernel where I introduce the spatio-temporal component and then the weights depend on this. So I'm modeling this variable here, and I'm trying to transfer the spatio-temporal dependence on the weights. However, I'm modeling this variable, and then I'm transforming these variables into weights with respect to this construction. So there is a difference between the dependence that I'm imposing to these variables and the dependence that I'm imposing to the weights. And I've done some work about this. So for example, if I'm creating, so these are the V variables, and I'm creating a type of relationship between two locations. If I transfer these dependence, so I see, for example, that here, these two components are almost independent. Because there are no clear patterns. If I transform these V variables into the weight, so the pi variables, I see that these pi2 and pi3 are much more correlated than the initial variables. So it's true that I'm creating some dependence among the weights as well, but I'm also modifying that dependence with the stick breaking construction. So this is something that to take into account, in particular if the goal is not prediction but clustering. So we had a solution with some collaborator of mine in this paper for finite mixtures, but we haven't reached a solution for infinite mixtures yet. So thank you very much for listening today. There is a couple of works like I've presented that are still in progress. Hopefully there will be online soon, but I'm happy to get any question that you may have.